Tonight I'll be discussing a methodology of data collection that utilizes OpenStreetMap, which is an online platform to store open data. My research considers how communities and built environment professionals can be involved in this methodology of data collection and how that can benefit post-disaster decision making. I need to emphasize that this methodology really pertains to developing countries which lack existing geo-reference data. So data is often communicated in maps and PDF reports. While this is necessary to visualize and convey data on a spatial scale, the actual raw data behind these images is inaccessible or closed. So it's kind of a look but don't use policy for sharing data. This means you can't access the data to use it or visualize it in a different way. In fact, data is often not available for analysis, efforts are duplicated, and by not sharing data, it soon grows out of date. Furthermore, weak data sharing arrangements and high transaction costs make it hard to gather fragmented data so that chances for collaboration are hindered or not recognized. Data is required to understand risk, as this formula shows. You must know the hazards that affect an area and what the vulnerability or exposure of the area is to those hazards. For instance, these images show a hurricane hazard, a vulnerable fishing village, and the risk of damage. With effective mitigation and adaptation, the risk is reduced. So determining hazards and structural information enables risk assessments that can identify vulnerabilities. This in turn facilitates the development of contingency plans and guides the implementation of pre-disaster mitigation and adaptation efforts. My research then considers where the community and built environment professionals fit into this framework with a focus on the top corner there, the contingency plans. A disaster management contingency plan uses a disaster scenario to outline necessary response procedures, roles, and responsibilities. It improves the quality of a humanitarian response by enhancing the effectiveness, appropriateness, and timeliness of the response. While it is intended to inform decision-making immediately before and after an event, certain aspects of early recovery can also be taken into consideration. So a good contingency plan improves the chances of good decision-making. So there is a need for open access to quality data in order to enable this. I recognize there's various alternatives out there, and many of you may question this methodology, especially if you think it challenges Google Earth, because a lot of us use it. However, the main point here is the concept of free and open access to raw data, which is something that Google Earth doesn't provide right now. OpenStreetMap was invented here at UCL in 2004 by Steve Coast, and was assisted by Professor Mookie Hackley, who is still here carrying out OSM-related research. OpenStreetMap is a volunteer mapping community that crowdsources data. It therefore acts as an open, accessible central data repository, and anyone can register an account to edit and download the data. So here there's students in Nepal. This is the project I was working on, and they're collecting data. And through this participatory mapping, the community increases its awareness of local risk vulnerabilities. By including built environment professionals in this data collection and contingency planning, they can contribute their knowledge and skill set to enhance the benefits of this methodology. This is the most important slide because this shows the type of data that can be collected. The blue outline is the building footprint, and so this is actually geo-reference data. It shows the sort of material that that building is actually built, the number of floors, and you can really add any sort of data to any point that's added to the map. So because the data is open and accessible, any organization is able to download what they need onto GIS software, such as shown here. The GIS can then perform queries and analyze spatial relations. This 3D image is an example of the possible visualization of data collected in Dhaka. This is of course dependent on the amount and quality of the data available. Similarly, data can be entered to risk analysis software, as you see here. This is a flood simulation screenshot from software called InnoSafe, which performs scenario-based probabilistic risk assessments. This shows a visualization of a flood extent and relevant data on the disaster. And InnoSafe produces questions that decision makers should consider. For example, which hospitals should be evacuated. So to clarify again, this methodology is already in use. Therefore, my research is simply considering where built environment professionals can provide input into the system. So Humanitarian OpenStreetMap Team, they utilize it in a variety of ways. The World Bank and GFDRR are involved with some certain pilot projects, and they're promoting the methodology among NGOs and governments. Map Action is a volunteer group of GIS professionals trained in disaster response, and they travel to disaster sites and use any available data, which includes the OpenStreetMap data, to make maps that provide a shared operational picture for all agencies engaged in the response. Crisis Mappers is an international community of remote mappers who, among other activities, use various online tools, including OpenStreetMap, in post-disaster situations to extract meaningful real-time data and update OpenStreetMap to assist agencies on the ground. This is a screenshot of Tackleban on OpenStreetMap. So it's recognized, this is a slide from, thank you Victoria, when a disaster event occurs, decision makers have a limited amount of time to make an increased amount of decisions, and these decisions in turn require an increased amount of data and resources. So my research will seek to identify the current amount of data that's collected and identify opportunities where urban planners, architects, and engineers can provide input when using the described methodology. According to previous research completed by the Max Lock Center, the following potential roles of architects, engineers, and planners have been identified in pre-disaster planning. In the risk assessment, architects have the skills to assess local construction techniques and the uses of houses and community facilities. In mitigation and adaptation, they can advise on the planning of community shelters and dwellings, and in contingency planning, they are able to provide advice on building uses in the event of a disaster. Engineers are then well positioned to assess the stability and vulnerability of existing structures and identify failure modes and consequences in the risk assessment. In designing mitigation and adaptation projects, they can specify structural requirements and identify post-disaster response mechanisms. As input to contingency plans, they can specify measures for providing temporary strengthening of existing structures, identify vulnerable structures, and measures to be taken in the event of damage to buildings. Finally, with planners, we're well positioned to provide input to risk assessments by estimating vulnerability relating to the new way land is used in settlements, buildings, and infrastructure are located. Can also access potential access issues during a disaster, and when planning mitigation and adaptation efforts, planners can identify the risk associated with certain areas, advice on risk reduction, and plan for quality development in the right locations. Finally, their skills are valuable in contingency planning to advise on relocation measures, and I am losing my spot here on the slides. I'll skip ahead and just back to that frequently asked questions. I think, as I discussed with Victoria this morning, I've covered quite a large subject area, and so there's actually quite a few obvious questions that people might ask, and I've presented this many times before with a different format and lots more time. So if anyone has any questions, especially on the validity of the data, then I'd be happy to answer those afterwards. Thanks very much.